as Bill mentioned, I'm going to be talking about causal inference in machine learning and data science. So this is the outline of the talk. I'll start by giving a couple examples for why causality is important. I hope this will demonstrate that as we go around doing data science and machine learning modeling, for many applications, understanding causal relationships and thinking about causal inference is crucial. After that, I'll talk a little bit about what is causality. And in this case, I'll be focusing on a particular framework called structural causal modeling. And then after that, I will talk a little bit about how to estimate causal quantities. I'm not going to go into great depth here, given the limited amount of time, but hopefully this will give everybody a little preview into some of the techniques that we can use to estimate causal quantities, and then kind of give everybody the impetus to do a little bit more research into the area and learn more. After that, I'll give a couple real-world examples from my work in data science at Brex. And this hopefully will make the techniques I talked about in the previous section more concrete. Okay, so I'll start with this motivating example here. Suppose you have a group of sick patients and they're given the option to try a new drug. And here's a bunch of data that we've collected, right? So we collected data on the participants, we collected data on whether they took the drug or not. And then also check their cholesterol levels, because we know that cholesterol is associated with outcomes in this case. And finally, we collected data on whether the patients recovered or not. So the question here is, based on this data, should the patients be taking the drug or not if they're sick? And I'll see if I can make this somewhat interactive and open it up and see if there's any responses in the chat. Is it just Q&A now, or is it? I see there is a chat here. Okay, great. Okay, so if anybody has thoughts on whether these patients should be taking the drug or not, feel free to leave a response in the chat. Otherwise, I'll just continue. Okay. Someone said no. Okay. So in this case, one of the things you'll notice here that's very interesting is that recovery is correlated, or recovery is associated with taking the drug if you look at like high cholesterol patients and or low cholesterol patients, right? So if you have high cholesterol, then you're more likely to have recovered if you took the drug. If you have low cholesterol, you're more likely to have recovered if you took the drug. But once I look at the combined, then it actually reverses, right? So when I look at the combined data here, people who took the drug were actually less likely to recover than people who did not take the drug. So this is called Simpson's paradox. It's a statistical phenomenon where when you look at aggregate data, the correlation goes one way, but then as soon as you condition on a particular variable, and you control for a particular variable, that correlation actually reverses from what we saw before. So in this case, it's positive when I look at the cholesterol level, within cholesterol level, and then once I combine the data, it becomes negative. So this is kind of strange, and it kind of befuddles statisticians for a while. All right, so the answer here actually depends on the underlying causal structure. So let's consider this scenario here. So suppose that for this particular disease, high cholesterol has a negative effect on recovery. In this case, doctors were more likely to prescribe the medication if the patient had high cholesterol. So in this case, cholesterol is a confounder. We should control for it. And what the data is telling is that the effect of the drug itself is actually positive, right? So what's happening here is that people are more likely to take the drug if they have high cholesterol, because the doctors are prescribing it to them, but they're also less likely to recover if they have high cholesterol. So in this case, like the correlation that we see, which is overall negative, right, between the drug and recovery, part of that is because most of the people who are taking the drug have high cholesterol and were less likely to recover in the first place. But the drug itself is actually helping. So once I control for cholesterol if I only look at people who have high or low cholesterol, so that cholesterol no longer is a source of variation in the data, right? The only thing that's varying now is whether they took the drug or not. And then I can see that the effect of the drug is actually positive, and the overall correlation is negative because of this confounder due to cholesterol. Right. But I'm going to give a different scenario that actually reverses the answer. So let's suppose in this case, the drug actually affects cholesterol, and that in turn affects recovery. So in this case, you can kind of see that what's happening here is the drug is raising cholesterol level, and then because it's raising cholesterol level, it's lowering the impact on recovery, even though it has a direct positive effect. So the drug may, but the way it works is like somehow it has a positive effect on recovery directly, but because it's raising cholesterol level, then it actually has a negative overall effect, right? And so if this is the overall causal structure, then I actually want to look at the aggregate data, because I want to take into account the fact that the drug is actually raising cholesterol, and then that also has a negative impact on recovery. So in this case, they should not be taking the drug, right? Because the drug has an overall negative effect through cholesterol. All right. So this is a final scenario where let's suppose that the drug should not be taken in combination with alcohol. So heavy drinkers avoid it. So alcohol affects whether you consume alcohol or not, affects whether you take the drug. Cholesterol actually has no effect on drug usage directly or recovery, but it's correlated with both. So it's correlated with drug usage, with taking the drug, because cholesterol is correlated with alcohol consumption, and then alcohol has an effect on whether you take the drug. Similarly, it's correlated with recovery because through exercise. So if you exercise more, it lowers your cholesterol, but exercising more also has a positive effect on recovery. So in this case, you can see that cholesterol is correlated with recovery through exercise, and it's also correlated with the drug, taking the drug or not, through alcohol consumption. And in this case, we'll come back to this one because it's not as simple to explain, but when I go through some of the techniques used in causal inference, we'll be able to see what the answer is. But I'd just like to emphasize from this example that the answer to this basic kind of question that we want to know on whether we should be taking this drug or not, and being able to answer that question from data really depends on some kind of understanding of the underlying causal structure. Depending on what that causal structure is, right, we get a completely different answer to this question of should I be taking the drug or not. So from the data alone, there's actually no way that we can answer that question. Okay, any questions so far? Cool. All right, so I'm going to go through a couple more examples, kind of illustrating how causality is important in some of these prevalent problems that we see in data science and machine learning. And this example here talks about explainability in machine learning. So this is kind of a hot area of research today, and a kind of controversial area where we've seen that a lot of these like deep learning type methods in particular are very, very effective at computer vision tasks, NLP, and other tasks as well. But there's concern that we don't really understand why they're good at it. And because we don't understand why they're good at these things, we don't necessarily trust the answers that they provide in kind of like high impact scenarios like self-driving cars, right? So we want to make sure that if we're going to deploy a machine learning vision system into a self-driving car, we have to be very, very certain that it's going to be a robust system, and we understand why it's kind of giving the predictions that it does. So here's one example that kind of, I think, illustrates how causality is a very important aspect in explainability of machine learning models. So back in like the late 90s, I guess, there was this study to evaluate machine learning in healthcare applications. And what they found was that a lot of these machine learning models were saying things that didn't make sense at first, right? So they found that asthma was associated with lower risk for pneumonia, even though doctors kind of knew from their own knowledge that asthma is a contributor to pneumonia. So because there were these sort of unexplainable or seemingly unexplainable correlations and predictions that they were getting from the models, they actually ended up rejecting neural networks, even though they had the lowest error rates. But once you got, so the reason why asthma was actually had a negative correlation with pneumonia was because of this underlying causal structure, where if you came into the hospital and you had asthma, then the doctors perceived you to be more at risk for pneumonia. And because of that, they ended up giving you more aggressive treatment. And because of that aggressive treatment, it actually ended up lowering the risk that you got pneumonia in the end. So once you had this kind of underlying causal explanation, and you're like, oh, okay, that makes sense to me. And I understand why that prediction is being made. Because they couldn't get that kind of explanation from neural networks, they ended up, not trusting them and not using them. Here's another example of another application or a kind of controversial area and hot topic in machine learning today that I think, I'm not going to give the answer to this question, but I think that any answer needs to account for causality in some way. And I hope that this example illustrates that. So in this case, just to give a little bit more background about fairness in machine learning, this is kind of like more for like applications that involve people, right? If you're deploying a machine learning model to say predict whether prison inmates who are up for parole, like what's their probability that they will commit a crime again on the outside world. This was actually a machine learning exercise that was done. I forget the paper or the research, but you can probably Google it fairly easily. And if you're going to actually deploy a machine learning model for something like, should I give parole to a particular prisoner, it needs to be fair with respect to, we need to make sure that it's not a biased machine learning model. I work in the credit card industry, and similarly, we need to make sure that our models are not going to discriminate essentially under particular protected attributes by law, right? So that's just to give a little bit more context. But this example here, we had this study back in 1975 that found that male applicants were actually admitted to UC Berkeley at a higher rate than female applicants. So they were accused of discrimination in this case, and there was a study done to kind of shed light on that. So the interesting thing, though, was that female applicants were admitted at a higher rate than males when you controlled for department on average. So this is another example of Simpson's paradox, right? Where when you looked at the aggregate overall data, you saw that male applicants were more likely to be admitted. But if you looked at an individual department, it turns out that the female applicants were actually more likely to be admitted. So what's going on here, right? It turns out that in this particular case, whether you were, what it turns out is that female applicants were actually applying to more difficult departments to get into, right? So because they were applying to more difficult departments to get into, those departments had a lower acceptance rate. And then when you've aggregated all of that data together, it turns out that that females were less likely to get in to UC Berkeley as a whole, but they were actually more likely to get into those more difficult departments and any kind of department they applied to on average. So in this case, what you see is that gender was not necessarily having an effect on admission. In other words, it wasn't really the case that UC Berkeley was looking at gender and saying, based on gender, I'm going to admit you or not admit you. But instead, gender was having an effect on the department that you chose. Sorry, there's a question here. Sorry, but shouldn't there have been a weighting by department? So in this case, I guess my question is, what do you mean by weighting by department? So, okay, so when you look at the aggregate data, it is essentially weighted by department size. But because so you can kind of imagine a case where, let's say that all of the female applicants applied to a department that had a 1% acceptance rate, and then all of the males that applied to one that had 100% acceptance rate. In this case, or let me put it this way. Let's say that there's two departments, one with a 1% acceptance rate and then one with a 100% acceptance rate. And then all of the males that apply to the difficult department to get into, basically were rejected. And then in that case, what you would see is that the females got in at a higher rate because they got in at 1%, and then males got in at 0%. But then if I look overall, right, because the males, and then a lot of males maybe are applying to the one with the 50% acceptance rate. So they essentially have almost a 50% acceptance rate overall, while females have almost a 1% acceptance rate overall. So you can kind of see how like they may have had a higher acceptance rate within department, but then once I aggregate, even if it's weighted kind of by, or just, I mean, it's weighted essentially by the number of applicants, because you're just taking an overall average, right, across departments, weighted by the number of people, then you'll see that correlation reverses. Hopefully that answers the question. So in this particular case, what you had was that was kind of what was driving the negative correlation overall, rather than say gender having a direct effect on admission. Okay. Okay. We can come back to that question if I haven't fully answered it at the end. I'll continue for now. Thank you. Okay. So just to summarize here a little bit about what I was trying to cover in the first section, modern machine learning methods, they're able to learn very, very complex associations from data. So you can see sort of like that they can learn incredibly high dimensional associations. They can learn very, very non-linear relationships. And this is what's led to a lot of the amazing progress that we've seen in computer vision, NLP, and other classification purely predictive tasks. However, there are limits to inference from purely probabilistic or associational information. And I hope the examples that I've given in the previous section demonstrate that without understanding causal relationships, there are certain limitations to what you can do from data, period, right? So you cannot provide actionable recommendations a lot of times. So that was what I tried to show using the first Simpson's paradox example, where you needed to understand something about the underlying causal relationship to know whether this drug is helpful or not from data, right? That information about the underlying causal structure is just not present in that data set at all. It's only when you have this extra kind of causal knowledge that you're able to answer that question. Secondly, they may suffer from a lack of interpretability. So that was the example given around the evaluation of machine learning models for healthcare applications. And what we saw was that doctors were not willing to trust a machine learning model unless they were provided with some kind of causal explanation for the associations that were given in the data. The last example is around kind of the importance of understanding causal relationships for fairness. And then lastly, this will kind of hopefully become more clear in the next section, but they perform poorly in new but related environments. So this is kind of referring to the field of transfer learning, where you train a model using data collected in one environment, and then you want to use that model in a slightly different environment. And it's also a question of robustness, right? Like a lot of times when you collect data, it may not be exactly the same environment in which you deploy the model. So you want to make sure that your machine learning model will continue to behave well in a deployed environment versus the data gathering environment. And this is this area of research called transfer learning. Okay. All right, so that's the first section. I'll move now to describing what causality is. And this is the paradigm I'm going to be using here is called structural causal modeling. This was described in detail lately by my former advisor, Udaya Pearl, but it's really been used at least implicitly by a lot of social scientists and economists for decades, I would say. But let me describe it now in more detail. So, okay, so going back to that first example where we had cholesterol, drug, and recovery, and we're going back to the very first kind of structure in which cholesterol is a confounder. Here, what we see is that recovery is caused by both cholesterol and whether you take the drug or not. And then the drug is also one of the things that determines whether you take the drug is whether you have high or low cholesterol, because doctors are more likely to prescribe the drug if you have high cholesterol. So underlying this, if we want to formalize this kind of logic, what we're really saying is that recovery is some function of the two other variables here, right? So cholesterol and drug. So if I look here, I have R equals some function of cholesterol level and whether I took the drug or not. And then the last variable that it's a function of is this, what we call the error term. So this stands for all unobserved causes of recovery. So there's other things that may affect recovery, like how healthy you are to begin with, how severe the disease is for you, and all of these things may not be measured. And so because they're not measured, we're not really trying. We don't explicitly model that relationship, and we say that error term is a random variable that just represents all of these other things that may affect recovery, but we don't actually observe. Similarly, here we have that the drug, whether you take the drug or not, is some function of whether you have high or low cholesterol, and then all of the other things that may affect whether you take the drug, right? And then we summarize those other things using this random variable u sub d. So what you have here is these functions are actually deterministic if I knew the values of all of the variables involved, right? So that including those unobserved error terms. But because I don't observe them, it's a random variable, and I end up having this distribution generated by these functions over the variables that I'm collecting data on. But you can kind of think of this paradigm as saying it's analogous to saying that a coin flip is random, like the outcome of a coin flip is random, but it's only really random because I don't know the initial velocity at which it's leaving my thumb, and I don't know the initial the rate at which it's spinning. But if I knew all of those things, right, I could perfectly predict the outcome of the coin flip. So it's only because I don't have observed these causes of the outcome of the coin flip that makes it an actual random outcome. So that's kind of the underlying formalism that we're going to use to describe causality. Okay. So to make this a little bit more concrete, I'll go through an example here where, suppose we want to predict where a cannonball will land based on the initial angle of launch. So the typical machine learning approach here would be to collect a bunch of data where you have different angles at which the cannonball was launched initially. You have different speeds for that. You have, and then you collect the data and see how far that cannonball flew before it landed. And then you can take that data, you can do some kind of like nonlinear regression maybe, and then you can fit this function of all that data. And then moving forward, if somebody ever asks you, okay, like I'm going to launch this cannon at 30 degrees with this initial velocity, then what would be the outcome? And then you could just plug that into your regression and you get an answer for prediction, right? But underlying this data here is this kind of physical mechanism, which is essentially kind of how we can view structural equations, sort of like the physical mechanism that is underlying how these variables take on the values that they do, right? So this equation here is just derived from Newtonian mechanics, and we have that distance is this function of the direct causes of the distance, right? So it's a function of the velocity at which the cannonball leaves the cannon. It's a function of the angle of initial launch. It's a function of the gravitational constant. And then there may be like other things that we don't measure, right? So we don't measure, for example, like the wind speed or maybe like the effect of friction through the air of the cannon. So these sorts of things may result in a slight difference from what the first part of the equation says, but it's really just like all these other unmeasured variables, right? So if I compare these two sort of explanations for the data, right? So in one case, maybe I have a regression equation, and then the other case I have what's the actual underlying structural or causal mechanism that describes that data. I can see that there's a lot of things that I get from the structural equation that I don't get from, say, a regression equation, right? So I can predict the effects of actions that were never taken in the regression. So if I took these actions if I took the actions as I was collecting the data for the regression, I could probably do it. But if I didn't, then I can't. So what if I collected all the data on a single cannon and I never varied the velocity that the cannon fires the cannonball? In that case, the regression would not be able to actually tell me, what the effect of changing that velocity would be. but this equation does, right? So if I improve the cannon by increasing the initial velocity, then I know how that would affect the distance at which the cannonball flies. And then I can also predict the outcome of cannons in general, even on other planets, not just this cannon, right? So this is kind of related to transfer learning, where I might apply that cannon in a different environment to where I actually gathered the data. In this case, I just have to change maybe the gravitational constant, and then I can get a good sense of how that cannon would perform on another planet. And then finally, it not only kind of like describes that distance, but it really explains it. So I can answer questions like, why did the cannonball land 60 meters away? And using this equation, I can give a very satisfying answer where I say, well, it's because like the velocity was X when I launched it. I used like a 60-degree angle when I fired it, and I fired it on Earth. And so that's why it landed 60 meters away, right? Okay. All right, so let me just like now that I've kind of described like what causality is, I'm going to talk a little bit about the way in which we learn about causality from data and compare that to kind of what traditional statistics you would do with data, right? So traditional statistics, you make this assumption that there's an underlying probability distribution that generated this data, and from the data, I try to learn certain aspects of that distribution. So for example, maybe I've collected data on the heights of like many different people in America, and I might want to answer a question like, what's the expected what's the population mean for height in America? And that's a property of the distribution of height, right? So it's just the expected value of the height. That might be one thing that I try to get using traditional statistics from data. Another example might be, maybe I want to learn something about a joint distribution. So maybe I want to understand like just the probability that a patient will recover given they took the drug. And note that this is not the same thing as the probability that a patient recovers if I force them to take the drug or not, right? Because what we saw in the first example was that whether they take the drug or not also depends on their cholesterol level, at least on that very, very first example. And so whether I just can do this condition and see the correlation overall of recovery on the drug is different from actually the causal effect, right? But traditional statistics gives me like many ways to kind of understand this joint distribution. Maybe I can do a regression, right? That tells me the expected value of recovery given different values of taking the drugs, and that is binary variable, so it's simple. But there's all sorts of different techniques for me to understand like these aspects of the distribution. Okay. So going to more of a causal inference paradigm, what we want, in this case, we want to estimate aspects of the underlying data generating model. So what we saw before was like causal effects, like if I prescribe the medication to a patient. So in this case, now I'm no longer allowing like whether they take the drug to be determined by cholesterol, but if I just say, I have this patient and I just like tell them, should I take the drug, should you take the drug or not? That's, we call that probability of recovery given due taking the due D in this case, rather than just R given D. So this is kind of the difference between just observing versus going in and enforcing an intervention like taking the drug, or a policy like taking the drug. So what we saw before was like this is a property of the underlying structural equations, right? So this is not a property of the distribution anymore, because I could never get that information just from the distribution, but I could get it from the underlying structural model. And I can also, another type of property of the structural causal model that I can get are counterfactual. So that was the example of like, given that the cannonball landed 50 meters away on Earth, how far would it have gone if I had fired it on Mars? So what I can do now is I can, like, based on the fact that it landed 50 meters away, I can kind of get a sense of whether what angle it was launched at and the velocity, and then I can apply that on Mars, and I can actually get an expected value, for example, of how far that cannonball would have landed on Mars rather than Earth. This is another property of the underlying structural equations that I can derive. But I don't always have like the full description of those structural equations, right? So instead, what I want to do is answer these questions from the underlying model in the same way that when I answer the question of what's the average height of Americans, that's something that I can answer. So from the data, but I don't have the full joint distribution to begin with. I'm just trying to answer this aspect of the distribution from data. And in this case, I try to answer these aspects of the underlying structural causal model from data. Okay, so how can we actually do that now? And in this section, I'll go over some techniques for how we can actually get these sort of causal quantities from data. Okay. So I'll start with another example here. In this case, we've done studies that have demonstrated that there's a correlation between eating red meat and getting colorectal cancer. So, but the real question is, does this mean that if I reduce my red meat consumption or increase my red meat consumption, that will actually have an effect on whether I get cancer or not? And, oh, sorry, so there's another question here. Do you feel neural networks are being overused as silver bullet and feature selection is becoming a lost art? That's an interesting question. I'll take that one at the end since it's not directly relevant to what I'm talking about right now, but I will come back to that when if we have time at the end. Thank you. Okay. So in this case, I don't care, like necessarily just about this correlation. I really care about whether I should be changing my habits and whether I should be eating more or less red meat, right? Okay. So in what ways might that correlation actually not be might not actually be indicative of the effect of eating red meat on cancer, right? And so we know, for example, that red meat consumption is correlated with other dietary risk factors. So people who eat a lot of red meat, they tend to eat less fruits and vegetables. They tend to eat fattier foods in general. They're more likely to drink alcohol. It's also correlated with behavioral risk factors like low physical activity. They tend to smoke more, and they tend to exercise less. So is it the case that eating red meat is actually what's driving this correlation? Or is it the case that, that it's these other factors which are associated with red meat that are actually causing the cancer? And it doesn't actually matter whether I eat red meat or not. Red meat is a good signal of whether somebody might get cancer, but it doesn't tell me, whether I should eat more or less red meat, because it's actually these other things that may be causing cancer. So if this is the underlying causal structure where I have red meat consumption, I want to know the effect of this edge. How strong is this edge? Is it 0 or is it larger? But the problem is that there are unobserved latent confounders, right? So there are other things that are associated with red meat consumption and are also associated with. There's basically common causes of both of them. So that means there's the presence of some kind of confounding, but so in this case, it's the dietary risk factors, the behavioral risk factors, which sort of, so this double-edged, bidirected edge here in the graph symbolizes that there's some kind of common cause of these two variables that I don't observe. And in this case, it's D and B, the dietary risk factors and the behavioral risk factors. And since I haven't collected any data of that, I not actually answer this question. So I don't know how much of this correlation is due to the effect of red meat on cancer versus this confounding relationship. And because I haven't, yeah, in this case, well, we call this the problem of identification. Like, can we estimate the causal quantity from data? And if so, how? And in this case, the answer is like, you just cannot, because there's no way for me to disentangle these two contributors to the correlation and understand how much of it is due to red meat on cancer. So we'd say it's not identified. All right. Okay, so however, if the data on dietary risk factors was available, and if I did collect the data on all those behavioral risk factors, so if in addition to collecting data on red meat consumption and cancer, I collected data on how much fruits and vegetables these people consume, how much they tend to eat fatty foods, etc., then what I can do is actually control for it, right? So let's say that this is the underlying causal structure now, where food preferences, in this case, causes whether I eat red meat. It also causes whether I have other dietary risk factors. And then there's also these behavioral risk factors, but I know there's latent common causes between both of these, right? So that's what this bidirected dotted edge means, that this could be like the culture in which you grew up. So the culture in which you grew up will affect your food preferences. It also affects, your behavior. So I kind of model that using this, these bidirected edges here, signifying that I think there may be some kind of latent common cause that I'm not accounting for. And in this case, I can actually estimate the effect of red meat on cancer. So if I control for dietary risk factors, I control for behavioral risk factors, then I basically block the correlation that I get through these confounders. So this intuitively, I can kind of see from the graph that there are two ways for red meat and cancer, or actually there's three ways for red meat and cancer to be correlated. One is through the direct effect, but there's also these other like kind of paths that go through other confounding variables, right? And what we see in the graph here is like that these are essentially blocked by these dietary risk factors and behavioral risk factors. And so if I actually kind of control for them, I can block these confounding paths, and all that's left is the correlation between red meat and cancer. And then I'll make this a little bit more explicit in the next slide, what it kind of means for these paths to be open or blocked. And you can kind of think of like open paths through the graph as transmitting correlation or dependency, and then blocked paths do not. So how can I kind of see that from a graph? There's this technique called deseparation, and that's what I'll describe here. So basically what you have here is that any path in the graph will generate correlation through it unless there's these two colliding arrowheads. So in this case, with like burglary, let's say that you have a house alarm that activates, and it also activates when there's an earthquake. In that case, like they both cause the alarm, but that doesn't mean they're going to be correlated with one another. These are essentially independent events. So you can see that this kind of path through the graph does not transmit correlation. Now, any other kinds of paths, like so, for example, like if there's a direct causal path, like from temperature, as the outside temperature goes up, increases water activities, which also increases the number of drownings that happen. So I can see that there will be kind of a dependency that's transmitted along this type of path, and it's also transmitted along this type of path when the tails of the arrowheads are connected to one another, right? So in this case, you have ice cream sales go up when the temperature goes up, water activities goes up when the temperature goes up, and drownings goes up when the temperature goes up. So in this case, you can see that actually like ice cream sales will go up when drownings go up as well. So you're going to see like this correlation between ice cream sales and drowning through this sort of path here. Okay, so once I start conditioning on variables, I can either open or close these paths. So if I say like condition on temperature, right? Now all of a sudden, ice cream sales and drownings are no longer going to be correlated, right? So if I only look at days with high temperature, then there may be certain reasons why like people will buy more or less ice cream on a given day with high temperature, and there may be more or less water activities on those days. But that source of variation of temperature no longer exists, right? Because I'm only looking at temperature days with the same temperature. And if that's the case, you're not going to see this ice cream sales and drownings correlation any longer, because that was really what was driving this sort of correlation that I saw. Similarly, if I actually controlled for water activities, so if I control for water activities along this path, I would also block it, right? So if I look at days with the same amount of water activity, then you're not going to see this correlation between ice cream sales and drownings any longer. But the opposite actually happens on this sort of what we call a collider path. So this is a collider path because the arrowheads essentially collide at alarm. And what you'll actually see is if you actually condition on alarm when on a collider, it will actually generate correlation between the things kind of on each side of the collider. So if you think about this, like let's say that I know the alarm went off. If I know the alarm went off, then let me put it this way. Yeah, so if the alarm goes off and I know there was a burglary, it actually like decreases the probability that there was an earthquake, right? So like it kind of essentially explains it away. So when I actually observe cases where the alarm went off, then there is actually a negative correlation between burglary and earthquake, because each one kind of explains the other way. If the alarm goes off and I know there was an earthquake, it actually reduces my belief that there was a burglary, because I kind of know it was actually probably the earthquake that set it off. This is kind of like a more like Bayesian-oriented explanation. the other thing that opens a collider is any kind of descendant path on the collider as well. So let's say you have an effect of the collider, like police arrive. Then if I know that the police arrive, and then I know there was an earthquake, then it actually decreases the probability of a burglary as well. It's kind of like a indicator that the alarm went off. So even if I don't know that the alarm went off, if there's some kind of indicator that the alarm went off, then it's very similar to me having observed the alarm as well. So just to summarize here, like collider paths do not transmit correlation between them, but as soon as I actually condition on the collider, or I control for the collider, or an effect of the collider, then it actually does open up the correlation and dependency between along that path. Okay. So now going back to sort of these examples that I gave earlier, where we kind of talked about how controlling for confounders allows you to estimate a causal effect. So this backdoor criterion here is a graphical criterion where if you're given the actual graph as an underlying causal structure, then it will tell you like what variables you need to control for in order to get the causal effect that you want. And basically the idea is a backdoor path between, say, a cause and effect that you want to measure is just any path that starts with an arrow into both of them, right? So you have this path that has an arrow going into drug, and it ends with an arrow going into recovery. That's what we call a backdoor path. And essentially, you just want to block all of those backdoor paths, right? So in this case, if I control for cholesterol, I condition on cholesterol, it will block that backdoor path. And then what I'm left with is this direct causal effect, which is what I want to actually measure. So that's how I can kind of confirm from the graph that this is like a variable I need to control for, or it's the variable I shouldn't control for, or I don't need to control for. There's a couple caveats to this, and that is that you should never control for any effects of drug. And that includes any effects of recovery, right? So anything that is, since the drug affects recovery in this case, anything that's also like an effect of recovery you shouldn't control for, it will actually bias your effect. All right, so in this example, I can see that controlling for cholesterol blocks all backdoor paths. In this example, I can see that controlling for dietary risk factors and behavioral risk factors blocks all backdoor paths. And I just want to note, like just to make this whole collider thing a little more explicit here, if I control for dietary risk factors here, I actually open this backdoor path like this, right? So this backdoor path ends up being open because it's a collider, and this is a descendant of a collider. So if I control for this, it actually opens this backdoor path. So I would have to also, but once I control for behavioral risk factors, I end up blocking that backdoor path because that's not a collider. Okay. So now I'm going to go back to that first example that I said, is not a very obvious example, and not an easy one to explain, but we can see now from this graph that controlling for cholesterol would give you the wrong answer in this example on the left here. So on this example on the left, what I can see is if I control for cholesterol, I actually open up this backdoor path, right? And I actually induce bias by doing that. So the right answer is to not control for cholesterol, because if I don't control for cholesterol, then this path is not open. I think this is an interesting example because since people have been trying to understand causal effects from data, which is since pretty much correlation was discovered, right? Like as soon as you see correlation, the natural human inclination is to try to draw causal inference from it. And what a lot of people realize is like, this is like a pretty kind of straightforward and obvious example where you kind of think, oh, if there's this common cause, this confounder, then I just need to control for that confounder. And there was a lot of attempts to kind of define what a confounder is as being something that is correlated with the drug, or correlated with the treatment in this case, and also correlated with the outcome, right? And in this case, cholesterol is correlated with both, but it's actually not a confounder. I should not be controlling for cholesterol at all. So this is kind of if you kind of look at the history of like how people try to do causal inference, this example is kind of something that would be very surprising to people who are not aware of confounder paths, or collider paths, I'm sorry. Okay. All right, since we're a little bit short on time, I think I can I'll skip this one for now, and then I'll just go into the examples. This is just to briefly describe it, instrumental variables is another technique that I can use to estimate causal effects when I can't control for confounding. So if you see like this example here, you have a confounder here. So there's like no way I can control. I want to know the effect of X on Y. There's no way I can actually know the effect of X on Y by controlling for the confounders, because I just don't observe those confounders. I haven't collected data on them. So if I have something called an instrumental variable, which essentially has this structure here, then I can still estimate the causal effect under certain parametric assumptions. But I'm going to skip this for now and just kind of keep going. Okay. All right. So to summarize what I've discussed so far, this is kind of like a basic causal roadmap. It can be more complicated when you want to think about things like missing data or like if you have selection bias issues. But this is sort of like kind of a basic roadmap for how you can estimate causal effects. So first, you need to define the causal model over the available data. So essentially, in this case, we've been using a graph. But no matter what, you need to have some kind of causal knowledge or causal assumption in order to make causal inference. And that's what we saw in the first example, right? Without having that kind of at least basic understanding of the underlying causal structure, we can't actually infer what the causal effect is. All right, so in this case, we've been using graphs as our causal model. And then we express the query as a causal quantity in terms of that graph. So I think I haven't been very explicit about this, but I like them sort of saying, in this case, on the left, we see the causal graph. This is the structural equation.
I think the speaker somehow got disconnected. He will rejoin shortly. Oh, hey, Ryan.
Hey, sorry, I seem to have lost Wi-Fi, so I'm on my phone now.
Okay, no problem. I think you can. Can you still share your screen?
I can't because that's on my laptop.
Oh, okay.
Yeah, I think what I could do maybe is open it up to questions for now. I have a couple more slides of like real world examples.
Sure.
Yeah, if I get my internet back, I can maybe finish that. But I could
okay,
for now.
No problem.
I'll just open it up to questions.
Okay, yeah. No problem. Yeah, let's. Well, again, thanks for connecting back. So let's just go through the, can you see the Q&A, the chat? You should be able to see it on your screen, from your phone, right?
Yeah, I don't see it. Maybe there's, let me see where I can find it. Oh, here it is. I see it. Okay. No, that's not right. I see it now though. Okay, chat.
Yes, in the chat.
Oh, I could try pointing it. Yeah, that's true too. Someone suggested that I point my phone camera at the computer. Should I do that, or let's see. Okay, I can probably try just wrapping it up quickly and then opening it to questions.
Okay.
Okay, so I don't know if this you can see this. Does this work, or does this not really work?
No, right now I think your screen still freezed.
Oh, okay. Maybe I can just take questions then. Keep it simple, and then I can if it comes back, I'll see if I can go through the last examples. I could also share the slides with you.
Okay.
If you
Yes. Please share the slide with me, and I think you also can turn off your camera. I think just to make the
Yep.
language much better. Sure. Okay. So can you see this? Can you see the questions in the chat?
Yeah, I think somebody earlier. I don't see the previous questions anymore, but I think somebody had asked.
Oh yeah, you rejoined. Okay. Let me see which one. Okay, yeah. Hold on. I think let me read the question to you if you. Okay. I think this one is already been answered. Let me copy paste these questions.
Okay, so while you're pulling that back up again, I can answer some of the other questions. So one of them, I think I'll start with, where can I see more practical examples of this, including code? I have, in my last slide, I actually have some recommended reading. So if we can share the slides, you'll be able to see that, but I'll tell you where you can see some more practical examples. There's, my advisor wrote this book called The Book of Why recently, which I think is, it's not as much like a textbook. It's a little bit more like kind of like a pop sci book, but not quite exactly either. So it's very readable. It's very easy to read. I think it's very entertaining. And there's a couple of software packages that build off of that and basically show the examples in that book. And so, for example, one of them is called causalfusion.net. This is I think that's still in beta. It's one of my collaborators when research collaborators. So it's a software package that he created. But I think you can sign up for the beta. There's also one called Pyagrum, Pyagrum. And again, these are in the slides, so you can see them when I share them. And so those are two software packages. In terms of additional reading, there's a textbook that my advisor wrote called Causal Inference and Statistics. I think that's a good place to start. It sort of talks about graphical tools for causal inference. There's also some going along like kind of different ways to do causal inference outside of the causal graph community. There's a book called Mastering Metrics by economists that talk about some of the techniques that economists have used for a long time to do causal inference. And there's also code associated with that book. Yeah. Okay, so what was the question about neural networks? Oh, here it is. I think it's put up here again. Do you feel neural networks are being overused as a silver bullet and feature selection is becoming a lost art? So I think that, I think neural networks, feature selection neural networks, these are kind of, I don't know if I feel like that feature selection is becoming a lost art. I think like at least in the data science that the practical examples that I've had in my career, I think feature selection is still really, really important. And particularly with more like business analytics type use cases. I feel that neural networks they work best with like highly unstructured data. So for example, like images or speech or language, which is it's not structured, and it's very difficult to like do feature engineering on that type of data, right? So for example, like if I want to train a machine learning model to be able to recognize an image of a dog, right? It's very difficult to specify the features of a dog. So it's very difficult to say like, oh, I want like a certain kind of snout, because some dogs don't have snouts, right? And they're very different in how they look. And then you have other animals that have similar snouts. It's really, really difficult to do feature engineering on something like on that type of data. And neural networks are kind of meant to learn those features on their own. So they like, you know, you specify the architecture, and then from that architecture, it kind of learns those features on their own, and it's able to learn. It does quite a good job. It does better than anything else that today that on those types of applications, right? Like with very highly unstructured data. But I think that for a lot more structured data applications, we've seen that they don't perform as well as some other techniques. I think like a lot of forest type techniques tend to perform better. So, and in that case, you know, feature engineering is still really important. So I don't know if I totally agree with it becoming kind of a lost art. I think that neural networks have gotten a lot of hype because they've been able to solve these problems that AI hasn't been able to solve for a long time. But it's not something like, it's definitely not a silver bullet that, so I agree that it is maybe overhyped that in the media as like the silver bullet that solves AI for everything. It's not true at all. So I would say that. Okay. Let's see, what's the next question? Are SMEs or becoming one yourself the only way to determine colliding and or confounding paths? So I think that having an SME or subject matter expert is definitely the easiest. It's a good way to do it for sure. There's definitely other ways. So if you can run randomized control trials, then you like at will, basically, then you don't really need to. So for example, like in technology today, A/B testing is really prevalent, and that's essentially running randomized control trials, right? So if I can run like randomized control trials on all of the causal effects that I want, then I don't need to have like a subject matter expert to explain the underlying data structure, the underlying causal structure. And that's actually because I know the underlying causal structure because I'm the one generating the data. So the data is no longer like observational data that's generated by, at least on the treatment, right? It's no longer generated by like whether cholesterol no longer affects whether you take the drug or not. In a randomized control trial, I'm the one deciding who takes the drug and I'm randomizing it. So I actually have that knowledge kind of built in because I'm generating the data. So the answer, I think, is like if you're doing an observational study, then having a subject matter expert is really important. But if you can run like A/B tests and you can run like randomized control trials, it's not necessary. There's also like there's a literature on like learning causal structure just from data, but it's like kind of one of the things around that is you cannot fully learn the causal structure in all cases. Like most of the time, what you end up is with like an equivalence, what they call an equivalence class of possible causal structures, all of which are compatible with the data. So you can kind of get some understanding of the underlying causal structure just from data. You can get what they call a skeleton, but you can't really get like the full underlying causal structure, and you usually can't like learn causal effects that you want from that. Okay. So let's see. Was curious to know how much time do I have, by the way?
Let's have a couple of minutes.
Couple more minutes. Okay. Cool.
Yeah.
Okay. So the next question was curious to know, how do you use causal inference for credit risk systems at work? So that's a good question. So actually, like one of the examples that I was going to show was it was kind of basically when we had at one point come up with a new credit policy essentially, and we wanted to do some testing of it, essentially A/B testing of it before we fully rolled it out to everyone. And so what we ended up doing here, but we also like I think partially because we're a B2B company, but also we try to be very customer focused, so we don't want to negatively impact customers through A/B testing. So I think, you know, so what we ended up doing with this new policy was actually we ran what was a biased randomized control trial where we made it more likely for you to be rolled out under the new policy if we kind of like thought it would be better for you. So clearly this kind of like biases the outcomes, right? Like it'll make the policy look better than what it actually is, because we're kind of selecting customers that are better for the policy onto the policy. But because I kind of generated that data myself, right? Like it's almost like running a randomized control trial, in that I'm actually deciding who goes onto the policy or not. And I know the decision-making criteria for how someone gets selected onto the policy versus they don't. And so that actually allows me to control for it. So I can use the backdoor criterion, actually. In this case, we use the backdoor criterion, and we actually do the adjustment to unbias the data. So that's like kind of one example. And hopefully, yeah, I didn't get to go through the slides, but I kind of tried to describe that in the slides a little bit. So once we share that, then hopefully like that'll become a little bit more clear. Okay, so maybe I can do one more question. Let's see, can was curious, no, doesn't come into view the quality of the initial, yeah, okay. So there's this question, doesn't it here come into view the quality of the initial business analysis / SME specification? That's definitely true. So like if your initial specification is wrong, then your answers will also be wrong. On the other hand, you cannot get answers without having some kind of specification in the beginning. So you need to be careful about that. There's different things that you can do to kind of make sure that your answer is correct. It's impossible to always like be fully sure, I would say, but there are certain things you can do. So there are algorithms, and actually a lot of my research was on deriving what we call testable implications of the model. So there's like certain ways you can actually test that specification. You can't fully test it to know like everything is correct, but there are certain things that you can test to kind of try to see whether they're correct. One way that's kind of, just to give one technique that's been used for a long time by social scientists and economists, is what we call like over-identification. So if you remember, the identification was like, how can I estimate this causal effect from the given causal model? But in some cases, I may be able to, from the given causal model, be able to identify the effect in two independent ways, essentially. And in that case, I have like two estimates for the causal effect that are based on different underlying